Okay, so let me start. So we were talking about the mathematical analysis of the frequency modulation. But before continuing for the same, that is the frequency modulation, today I'll be addressing again the part of AM. This is basically regarding the AM modulator and demodulator. So far, we have understood AM everything, the very basic concepts and mathematical analysis, the spectrum, and so on. But how to generate AM and how to recover the original signal from the AM, which is a demodulator, also called a detector, because we have to recover the same signal again. So I was thinking of having this modulator and demodulator after my FM signal, which we were continuing the basic concepts we have almost done. Mathematical analysis we're continuing, but because there is a lab tomorrow, and I came to know from certain TAs that if we could teach this thing, detector part and the modulator and demodulator in today's lecture, it will be a bit helpful. Otherwise, I would have thought of having it later. So I will have this lecture first, which is additional lecture on AM, which I thought I will do after FM, mathematical analysis, and then, but yes, we'll start with that, and then we'll continue with our FM after this lecture of modulator and demodulator. So I've already prepared a slide. The reason being it needs a little bit of diagrams and other thing and so on. But yes, it is the same way while I teach you. while I'm speaking. So you will not find anything discomfort also. So basically modulator means how we generate AM signal from my message signal, which is a low frequency signal, and a carrier signal, which is a high frequency signal. So they are the two inputs, and because of which I should get a AM signal. And then we have seen that AM signal is nothing, it is a double sideband signal with a carrier. But we have seen also that carrier doesn't carry any information, but lot of energy is wasted there. So we thought of having a double sideband suppressed carrier. That means only you will get the two sidebands, one lower sideband and the upper sideband. And then we have talked about the single sideband also. That means because the same information is contained in both the sideband, why to have the two sidebands? We can suppress one of them also. So I'll get a single sideband. So let's understand how we do this thing. This is, as I said, this is important for lab, but very, very and equally important for my theory lectures. So it was a part of the theory also. Okay. And sometimes we do appreciate that a theory followed by a practical is a good sign, but also other way also it is good. If you have done something in the practical and there you realize something which is not comfortable, it can be cleared in the theory later. So both ways are okay. And sometimes it is difficult to keep pace with the theory part as aligned to the practical part, because there may be some questions, I may go slow or maybe go fast. So there is always this tendency to not to perfectly align. That happens always. Okay, fine. So basically our first aim is to generate my single sideband signal, or let's start with a double sideband suppressed carrier. So for that, this is the circuit. Basically, here we apply a modulating signal input through a transformer. And then if you see here, we apply a carrier input also. 1 minute, sorry. So we apply a carrier input also and input message signal here. Okay. And then we use two FETs. These are the FETs, which is M1 and M2. Now, these two FETs are same FETs, means they are meshed FETs. That means they have the same values of whatever the various parameters of field effect transistor. And I think you must have already learned FETs are the field effect transistor. They are a better version of BJT. They can go up to high frequencies also. So it has three things: gate, drain, and source, and typically denoted as this one. It could be N channel or P channel, which you have learned also, but that we are not considering right now. So it is a simple two FETs, same type, identical type. So we say meshed FETs. And then we get the output here. And this is the supply that we give, the voltage that we apply to the FETs. Okay. Now, if you see here, let's understand what this circuit is about. So basically, we use two FETs, meshed FETs, identical FETs, and we apply modulating signal voltage, VMT, which is in the differential mode. So this we apply in the differential mode as seen in this figure. This is my input signal, which I'm applying in the differential mode. So there's VM there, there's VM down here, and which you must have learned in the thing. And your carrier signal, which is your VCT, is applied as a common mode signal. So this I'm applying as a common mode signal. So the two inputs are there. When we apply this signal in the two modes, then this signal applied at the gate of M1. If you see, this is the gate of the M1. The two transistors I have named as M1 and M2. This is the gate, this is the drain, this is the source. Okay. Gate, drain, and the source. So what we get the outputs here. So if we apply the signal at the gate of M1, it will be the sum of the two input voltages, VC plus VM. And the signal that we get in this one at the gate is VC minus VM. So basically we got these two signals which are applied at the gate of M1 and M2, which are the sum of the two voltages, my input voltages, which are carrier and a message. So it will be the sum and the difference. Then these two components are squared by the second terms of the transistor transfer function, because transistor has got a transfer function you must have learned in the basic electronics. So there we have got A plus B, V plus CV square plus DV cube and so on. So there is a second term which is squaring that. So these two components, which we'll understand in the next slide. So the common mode carrier signal is cancelled and I will get two drain currents. So I'll get two drain currents in the primary of the transformer, as we see in this figure. So this is the first slide is about the block diagram, the figure. Second one is just a small description, but the real thing we could understand this from this equation, what we have learned in the slide 2, or what we have described in that slide 2. So I have two voltages, VGS1 and VGS2. If you see here, VGS1 is this one, the gate to source voltage of transistor M1, and VGS2 is the gate source voltage of transistor M2. Okay, so your VGS1 is simply, if I see, is given as the sum of that two, VC plus VM, and VGS2 is given by VC minus VM. Then we have the two currents, as I said, and the transfer function, if we could write, the two currents are ID1 and ID2, which are shown here and here. Now these two currents basically can be written as the transfer function I0, which is the DC current, A VGS1 plus BG VGS square plus C VGS cube and D VGS4 and so on. But just we retain the up to the square terms. And similarly, ID2 is be written as the peak current I0 plus AG VGS2 plus VGS square. So I'm just highlighting this square part. That is very important. Other terms we could ignore it, the cube and the raised to power 4 and so on. So if I subtract 3 from 4, I get ID1 minus ID2, which is basically, if you see, these are the two currents which are there, and that will give me the DSP suppressed carrier output. Let's see how. So if I go this one, ID1 minus ID2 is given by, I simply subtract from 3 and 4. So I got this equation, A VGS minus 1 minus VGS2 and plus B VGS square, VGS1 square minus B VGS2 square. So I could write down the second part on the right hand side as, because A square minus B square is nothing, A plus B plus A minus B. So I got these VGS1 plus VGS2 and to VGS1 minus VGS2 and the B part. So straightforward, nothing is there. So this is the equation number 5. Now if I substitute 1 and 2 in 5, 1 and 2 is basically are my equation for VGS1 and VGS2. If I substitute these two equations 1 and 2 in 5, I will simply get like this, A twice of VM, because I'm subtracting from 1 and 2. So it becomes twice of VM. Okay, VC will cancel, VC minus plus VM minus VC plus VM. So it becomes twice of VM. And similarly here it becomes B twice of VC and twice of VM. Nothing great. So mathematically I could easily understand what I've written in the slide 2. So I 2A VM plus 4B VM VC. Okay. So here I get VM. Now I know what is my VM. It is VM cos omega mt, my message signal, and my VC is nothing. It is VC cos omega CT, which is my carrier signal. So I just replace small VM and small VC by the real signal. That means the frequency is also coming into that. So ID1 minus ID2, I could write down this as 2AVM cos omega mt plus I take out these common 4BVM VC cos omega C minus omega mt plus cos omega C plus omega mt. That means my output consists of my message signal. The first term is my message signal. The second term are the two side bands, omega C minus omega m and omega C plus omega m. So output contains my message signal, which was my original signal, and the two side bands. Carrier is absent. Now there is nothing like omega CT. Okay. In this equation number 7, the final equation that we got. So here carrier is absent. So basically I got double sideband and the suppressed carrier, and the message signal is also there. But I don't want the message signal right now because I have to generate a single sideband signal or double sideband suppressed carrier. So I have to remove this original message signal. Now, original message signal is at a lower frequency. As I said, message signal, your modulating signal is at a lower frequency. And so I just use a band pass filter to remove that particular frequency. Okay. So if my message frequency is say 10 kilohertz, carrier frequency is 100 kilohertz. If you see from this equation, I will get message frequency 10 kilohertz and two side frequencies 90 plus 90 and 110. That means 100 minus 10 and 100 plus 10. So I get three frequencies: original message signal 10 megahertz and two side frequencies 90 and 100. And obviously, if I want only the double sideband, the two frequencies, what I have to do? I have to remove the message signal. Okay. So if I remove the message signal, I have to use a band pass filter or a low pass filter. Band pass filter means targeting only the frequency of 10 megahertz, and then I will get double sideband suppressed carrier. That means 90 and 110. So 90 and 110. Again, if I want only 90 megahertz or 110 megahertz, again I will use one more band pass filter, which is centered at 90 or 110. Like the previously, I used a band pass filter centered around 10 megahertz. So that you go on using the filter once you get the specific frequencies and don't want that particular frequency, use the band pass filter, which will allow only that particular frequency to pass. Other frequencies will not be able to pass. So this is a simple method of generating a double sideband suppressed carrier. Okay. So once we got it, basically how to detect it? Because as I said, finally, it is like a child crossing the road. Okay. So I carry the child in my lap and cross the road. So that is modulation. And finally, I have to drop the child at the other end of the road. Okay. So that is called a demodulation or detection. That means the recovery. The child has now recovered to the same position that he was alone and he has already crossed the road. So that process is what we call the demodulation, or it is also in a simple way is called a detection. So demodulation or detection is the process of detecting or recovering the same message signal from AM signal. Because here I get the AM signal, which means there is a carrier, there are two side frequencies and so on. That is my original AM signal, which is a double sideband signal. So double sideband signal, as we have seen, it has got a carrier frequency and two side frequencies. Now I have to recover the original signal from there. How faithfully I recover? Because you have to recover exactly the same. Okay, it should not change. And that is, as I told you earlier, the faithful reproduction of the message frequency. Even if there are 10 frequencies are there, as I said, sometimes the message signal, like an orchestra, consists of 7 to 8 frequencies. Okay, so I have to recover all the frequencies. Then only you will be able to hear the orchestra very nicely. Okay, it should not happen that one of the frequencies is not recovered, like for the tabla. Then the whole sense of the orchestra will be not there, and you are missing something. So the fidelity is nothing; it is your ability to produce if there is only one message frequency, or if there are many, then all the frequencies are recovered. So we say hi-fi, Wi-Fi, so wireless fidelity, high frequency fidelity. So that is the common words we normally use, as I told you earlier. So also we have seen that if my message signal consists of one frequency only, the bandwidth required is twice of that message signal. That means twice of FM. So if I got a 5 kilohertz signal, we have seen the bandwidth required is twice of FM, because FC plus FM and FC minus FM, which gives me 2 into 5 kilohertz, that means 10 kilohertz. But if my message frequency consists of number of frequencies, say 3, 5, 7, 9 kilohertz, okay, like in an orchestra, it could happen, then my bandwidth required will be twice of highest frequency of the modulating signal. So that will become twice of 3, 5, 7, 9. Maximum value is 9. So twice of 9, that means 18 kilohertz. You can't say twice of 3 or twice of 5, because then you will be not detecting the other frequencies. Okay. So this is the fidelity that I have to recover all the frequencies. So it is a demodulation, I can say. It is a reverse process of the modulation. You just can't leave the signal modulated. At the receiver end or at your end, my signal has to be demodulated. Okay. So We normally use three types of detectors. One is what we call the peak detector. Peak, as the name suggests, it will only see the peak values. Okay. Envelope detector means it will detect the entire envelope, as we see later on. And there is a third detector, which is AM detector with AGC, automatic gain control. Of this, the envelope detector is the most common, but we'll discuss all the three and see what is the disadvantage of one with respect to the other. Obviously, envelope detector is an improved version of peak detector, as we'll see later on. And AM detector is an improved detector, another better version of the envelope detector. So this is the exercise that we'll be doing tomorrow. So I thought I will just explain to you the concept. So peak detector is nothing. It is basically a diode, as we have seen here, and a capacitor. So diode, we all know, it acts as a half-wave rectifier. Okay, you must have learned in the basic electronics. Half-wave rectifier, that means it allows only positive half of the cycle or negative half of the cycle. Let's say positive half of the cycle. So how that is possible? Because diode is a forward bias. So I can say diode is a on-off state. Diode has got a on-off state. A forward bias state is called a on state, and a reverse bias state is called a off state. So when I use a single diode, we know it acts as a half-wave rectifier. It will only allow the positive half of the cycle. Okay, and not allow the negative half of the cycle. So here, if you see, this is my AM input, which looks like this. Okay, because it is varying in the amplitude in accordance with the message signal. And the frequency that I shown here is the carrier frequency. So carrier frequency varied in accordance with the amplitude of the message signal. So at some places, my message signal was of high amplitude. So the carrier frequency amplitude also becomes like high. So this becomes my amplitude modulated signal. So that becomes my input. Okay, AM modulated signal, VAMT, which you have learned. It has got a carrier and the two side frequencies. Then we follow with a capacitor here and we measure the output. Now what happens here? This is the cycle which is my AM signal. I've shown in a bigger way here in the black color. Okay, but what will be the output will look like? Output will look like this, that there is a diode which is only allowing the half cycle, positive half cycle. That means I'm not showing any output or red color output in the negative half of the cycle. Okay, only positive half. Now here, what happens here? Your capacitor ka function kya hota hai? It charges, and then it should discharge. And discharging will happen. You need to provide a discharge path. But because it is a standalone capacitor, it only charges up to the maximum input voltage, which was the previous voltage. Okay, and it doesn't discharge. So I will get input like this. So here, if you see here, why the red color is there in the top half of the only, because the diode is a half-wave rectifier. So it allows only the positive half cycle. It will not allow the negative half of the cycle. Now, if you see here, this diode is capacitor is getting charged and it remains charged because there is no discharge path. It remains constant, as we see here in this value. It doesn't discharge. There is no discharge path available right now. So it remains the same. Then it goes to the next peak. It charges again and remains up to this voltage, which was the past input voltage, and remains constant here. And then again it goes to sees the next peak. It charges up to the next peak and remain constant, and then go like that. So we get it like this. So here, if I see, your output can never decrease with time because capacitor has no discharge path. Output is always, as we see here, the 0.3 which I've written, output is always equal to the maximum past value of the input. So this was the maximum past value of the input. So output remains the same. So it is a peak detector, and I am not getting the signal as I desire. It is like, yes, I am getting some signal, but it is input signal, but it is not the desired signal. So what we do here, we use envelope detector. Now, envelope detector is the same thing, that you have a diode and a capacitor. Now we also add a load resistor, and this load resistor is also called a bleed resistor. Bleeding. You say my hand is bleeding. That means blood is coming out. So bleed resistor means it is also called a bleeding resistor or a discharging resistor because it is helping in the discharge of the capacitor voltage. Previously, it was not getting discharged. My capacitor was assuming the maximum value, if you see here, and it remains same. It is remaining the same of the past value. Here, my past value of the input was this, and it remains same throughout. Then it rises to the peak again, and then the past value remains this and remains constant. So it is not following the envelope exactly, okay, of the message signal. So what we do here, we add a bleeding resistor, which is nearly of a very high value, because then only it will bleed fast. Okay. Now, if we do this, now what will happen here? My input signal, which was the same, but my difference here is that my output signal, which I've shown in the red color again, is that I got a discharge path. Previously, it used to be remain constant of the past value, but now it is getting discharging. It is also getting discharging. Again, it is getting discharging. Again, it is getting discharged. Sorry. So basically, now I am more closer to my the original message signal. Okay. So I got a capacitor which is discharging a resistor which is discharging my capacitor voltage. So it is not remaining constant. It is going down. Again, it is going down. Rather, previously it was like this. Previously it was like this. It was a constant. No, now it is not. It is like going down. Again, it is going down. Previously, had it been there, it should remain as a past value. So no. So now it is much more close to my this one. Then what we do here, still we have not got this thing. Okay. So what we do now, my output, if you see here, it consists of two parts. One is the DC value and the modulating signal at the output. Yes, I'm getting the modulating signal. It is not resembling as good as this one, because I've drawn in a slightly taking long cycles. But if you see the high frequency carrier, which I've shown in the black line, is a very high frequency carrier. It changes path, it changes the cycle very fast. Too many cycles are there. And too many cycles are there. There's this envelope, what we see in the red one, which is close to the message signal. It will look like this. So here my output consists of DC and my modulating signal. But I want the output to be totally modulating signal, no DC. Now, because it is a no DC I want, and here my output consists of DC and modulating signal, this experiment we will be doing tomorrow. So we basically, what we do, we add a capacitor. Okay, so before we go for that, how to remove the output, the DC which we got here. Sorry, in the previous slide. In the previous slide, as I said, now my output is also having certain DC and the modulating frequency. Finally, I have to remove the DC. But before going for that, what we do here, we understand the mathematics. Now, I have a resistor and I have a capacitor. Capacitor which is charging and a resistor which helps in discharging the capacitor voltage. Okay. So we all know that RC becomes your time constant. RC becomes your time constant. RC is nothing. It is basically a time constant. So capacitor is charging. C is the capacitor which is charging. R is the resistor which helps in discharging the capacitor voltage. So we all know that RC is a time constant. The important condition which should be matched here is that your message time period, because message signal is a frequency. Okay. So there is a corresponding time period for that. It must be greater than the RC, which is also a time constant, and it must be greater than the time constant of the carrier. Okay. Obviously, we know that the frequency of the carrier is highest. Okay. And the frequency of the message is lowest. So in frequency wise, it will turn the other way around. Okay. But let's talk about it in the terms of time, because RC is time constant. So T of message signal must be greater than RC, must be greater than the time of the carrier signal, where T is nothing, it is the time period. Now, message frequency, message time period is nothing, it is one of the message signal, 1 by FM. It must be greater than RC and it must be greater than 1 by FC. So let's say if tomorrow you are doing the experiment, first you see what is your message frequency and what is your carrier frequency. Corresponding to those frequencies, you find the time period. Like if I take the message frequency at 300 Hz, a low frequency message signal, modulating signal, the corresponding time period is quite large. FC, because it is a high frequency, 30 kilohertz, almost 1,000 times more. So here my uh, time period turns out to be smaller, and that is 33 microsecond. Okay. So I choose a resistor R, a very high value, because it need to bleed the voltage. I not should not be. Let's say I choose a R as 5.6 kilo or 10 kilo, and choose some value of C, but ensure that the condition, which is RC, which is nothing, it is time. So I choose 5.6 kilo ohm and 0.047 picofarad. Important thing is R should be high, and C could be a smaller value, but R should be high. So it becomes 5.6 into 10 to the power 3 into 0.047 microfarad. So it did 10 to the power minus 6. So that will give you the value in time constant. That is what we call the 263.2 microsecond. So 263 microsecond. So obviously with this RC value, my condition is satisfied. The T of message is greater than the RC, is greater than the T carrier. Okay. That means the discharge time constant, which is RC, is small as compared to the message signal. And it should be quite large as compared to the time period of the carrier signal. Okay. So this condition is must be satisfied. Because if RC is too large, then many cycles of the carrier are required to charge the capacitor to the full value. And if RC is too small, then my carrier will not charge even in one cycle. So there should be a compromise between the two. So as it's written here, if RC is too large as compared to the two carrier, too many cycles will be required. And if it's too small, then even my capacitor will not be able to fully charge in one cycle also. So this condition must be satisfied. It is in the terms of time period, but it can be expressed in terms of the frequency also, because T is inversely proportional to 1 by F, or in terms of the angular frequency also, 1 by 2 pi F, or and so on. So everywhere you have divide by 2 pi also. But this is the condition which we normally follow. That is important. So this condition, if it is followed, you will get a detect output, which we have seen, like what we have got here, something like this. So the capacitor is discharging. Because of the high value of the capacitor, it is fast discharging. Otherwise, slow discharge will be there. And my output consists of the DC and the modulating signal. Now I want to remove the DC also, because my aim is to get only the output. So what we do, we slightly improve upon this envelope detector by putting a capacitor, because we know the capacitor is a DC block. Capacitor is a DC block. So I just add a capacitor, which I've shown in the blue color. This is a coupling capacitor. Just look into this one. Don't see the green part right now. So this is a slightly better version of the envelope detector with blue part. Though I put this as a third type detector on third type of the detector, but right now consider only the blue part, not the green part. Okay. Now this additional capacitor I have read here. Capacitor, we all know, acts as a DC block. So previously what we got is a DC plus the modulating signal at this output. Now with this capacitor, your DC is blocked, and my output will consist of the modulating signal or the message signal. So I'll get something like a replica of my original message signal. Sometimes we further, so this is fine. This is fine. So up to the blue color, that means the coupling capacitor, which acts as a DC block, this is fine. There is now sometimes what happens here, when you get the message signal, okay, like what you are getting in a TV transmission, your volume remains constant throughout, and what you are getting there, signal is getting modulated at the radio station, and it is coming to your radio, which is a receiver, after modulation, and demodulation takes place at the receiver end, that is at your radio. Okay. Now what happens here? You must have noticed the signal that is coming, may vary with the amplitude. Sometimes the signal goes very high, volume becomes very high, sometimes the volume becomes very small. So we use something what we call it automatic gain control. So when you hear the TV transmission or the radio transmission, in all these things we have AGC, automatic gain control. Basically, it will help. Suppose my signal strength becomes very large because finally it is getting transmitted through a wire or through a wireless medium, air. And sometimes it rains, sometimes it snows, and sometimes goes in the various atmospheric condition from the retransmitting station to your radio as a receiver. So your signal may get attenuated or signal may get amplified, not amplified, attenuated smaller, or it may get attenuated to a larger extent. Attenuated means lost. Okay. So I will not like that type of the signal in my radio. That's sometimes if somebody is giving a broadcast, suddenly the volume goes high and suddenly the volume goes high. So there must be some automatic gain control also at my detection state, at my receiver state, which is in my radio, not in the transmitting station, the Doordarshan station. So I should have something for that also, so that my volume remains constant. So there we add a AGC filter. AGC filter is again a filter which consists of a series resistor RA. I have now changed it to RA. A stands for resistor for the AGC filter, and CA stands for the capacitor for the AGC filter. Like we have talked about CC for the coupling capacitor, and C and R the other normal values, the RC constant. So here, what will happen? This AGC filter, which consists of series resistor and a capacitor which is in shunt or parallel, we use this word. It will remove the modulating frequency component and constant DC level is obtained. Okay, so my signal will give me a constant level, which is desirable. I want. Same thing happens in my mobile phone also. There is a AGC because the signal that is getting transmitted, and if I'm calling you on the phone, it should remain the same. You may come close to the tower while speaking or while receiving, and it should not happen that your signal goes very high, and suddenly when you go into the basement or in the lift, it should not happen that the signal goes very down. I want to hear the same signal. So there is also a AGC there. So it will amplify the signal. If the signal strength goes down below with the two file names A and B. Okay, so separately I'll be doing this. Okay, so that you should not get confused why this sudden AM has come when we're doing this one. So the B part is the continuation of the previous lecture, but my recording will be the one. But these will be saved as the two PDF files because now I'll be writing this one. I saved it because I wanted to save the time also because of this additional thing which we have to finish before the tomorrow's lab. So I'll start a fresh file and let me do this. So I put the date today again. Today is so I'm putting as part B, and we will write as FM continued. From last lecture. So just to avoid any confusion. Okay. So these two files will be separately saved, and I will put it in the lecture folder, but the recording will be same, as it will continue to be the same file. Okay. So basically what we were discussing, we were talking about the mathematical analysis of FM. Okay. And we have seen that in the mathematical analysis, we have a function, what we call the sine of a sine function. Okay. Unlike in AM, where it is the product of two sine function. And product of the two sine function was very simple. Sine A sine B is equal to cos A plus B plus cos A minus B and so on. But here we get a sine of a sine function. Now, if I get a sine of a sine function, we were talking about how to solve this, and it can be solved. Am I right? Everything is visible? Am I audible also? I just wanted to reconfirm. Anyone of you, please?
Yes, sir. Yes.
Okay, fine. So then we said that it will be can be solved by Bessel function. So I'm just last time I definitely used, but I thought I will also talk about a Bessel function. So Bessel function is nothing. It is basically a function which is you not to mug up these things, but just simply look into this thing. It is a function of this form m cos beta. Okay, so it is a cos of a cos function, or sine of a sine function, or a function of another sinusoidal function. Okay, unlike cos A cos B, it is a cos of cos function. Okay, and it is defined as, okay, I think you must have done it, but if you've not done it, it's just, I will just explain to you. N is equal to minus infinity to 1 minute. I actually moved ahead last time, but I thought I will explain to you also a little bit of Bessel function, just to clear any doubts. But I explained it in a simple way as an application, but little bit I thought I will do more justice if I can explain little. So it is just given by J and M cos alpha plus n beta plus n pi by 2. That is the standard. No need to mug up. But this is when you must be learning the engineering maths, you will be encountering various functions to solve various trigonometric identities, Legendre, Bessel function, and so on. So for such identity where we encounter cos of a cos function, this is can be solved by a Bessel function. Okay, so just like what we had in this frequency modulation, and here my what we call the J and M is Bessel function of first kind and order n. Okay, and it is having an argument alpha is and beta. Okay, now this is the equation of a general Bessel function. Okay, if you recall in my expression, let me have the last lecture. I will just open the next slide. You will not be able to see, but I will be opening it. Let's see. But you can open in your last lecture also, so that 1 minute. Let me see. I could 15th of February. Yes. So if you recall, it is something which you were understanding. Okay. Now here, as I said, this is, if you compare this one, your alpha, if you recall, what was the expression last time we got it? VFMT. So recall that, which was there in the slide number 9. of the last lecture is equal to cos omega CT plus MF sine omega MT. Okay. That we have taken VC, though it was there earlier. So this was the, if you recall, the 9th slide. I've already that one of last lecture because the continuity was lost. So I thought I will put everything here. So this was the equation. Now, if you see here and compare with the previous equation, okay, let's compare this equation with the equation number, the Bessel function equation, which I have written here. Let's mark this equation A. Okay, so here, if you see here, I can write down this expression as if I compare this equation with the previous equation, you will find in A, alpha turns out to be omega CT and beta turns out to be omega MT. Okay. If I comparing with the above equation. So I could write down this, my expression for V FMT as, which was there VC also. 1 minute. In fact, you can bring VC also, though we have neglected, as I said, there is a VC component, but we have neglected it. So if you recall, I just neglected for the same, but you can have it also. VC sigma n equal to minus infinity to infinity J and M, okay, cos alpha was my omega CT, okay, plus n omega MT plus n pi by 2. I have already gone a step ahead last time, but just to make you understand, I'm just going for this also, how we actually equating the Bessel function here. Okay. So this is the thing which we have got. So here n is equal to 0 plus minus 1 plus minus 2. That is the Bessel function. So again, I write here n is equal to 0 plus minus 1 plus minus 2. So this is a standard Bessel equation. No need to mug up what I have written this Bessel function. But yes, just for your understanding, it has these components where J and M is the Bessel function of first kind and order n, and it has got the argument alpha and beta. Now, if I compare with my equation here, the cos part, the VC part, as I said, we could neglect it. As we have seen last time, I neglected it. So I will neglect it. So I just neglect this VC. So we can remove this also, nothing, but you can keep it also rather than writing this one. So it becomes like this. Okay. So it has also various terms, n equal to 0, plus minus 1, plus minus 2, and so on. So my equation becomes like this. Now we have to solve it. N can take the value from 0, then this term will become 0, the last term will become 0. Okay. So if I expand this for various values of n, I simply get an equation like this, which I will write for you. VFMT is equal to VC. As I said, I have already ignored it, but if you don't want to ignore it, you can keep it for the simplicity. So I could write down this as 1 minute. So the first term, let's start with the n equal to 0. So I will have my first term as J0, okay, M cos omega CT plus omega CT. That's all. 1 minute. If you see in the previous slide, I am now expanding this equation, which is the solution of my above equation using the Bessel function. So if I take n equal to 0, so this first equation becomes J0m cos omega ct. N omega m will become 0, n pi by 2 will become 0. So I got J0m cos omega ct. Okay, and that is my first term. Then we go to the second term. Okay, so I'll have many terms. Let's start with J1. I take J equal to 1, or n equal to 1, m cos omega c plus omega m t plus pi by 2. Then I take j minus 1 m, that means n I am taking minus 1. So it becomes cos omega c minus omega m t plus, or this will become minus pi by 2 because n pi by 2. So this becomes minus pi by 2. Okay. And then I have another term, just will use 5 terms only, J2m for n equal to 2. So it becomes cos omega c plus twice of omega mt. Because if you see this equation, it is n omega mt. It is n omega mt. So it becomes twice of omega mt. And this becomes twice of pi by 2 by 2. So it becomes pi. So it becomes pi. Okay. So that becomes my corresponding to n equal to 2. And then the last term. And we can have many more terms, but so it becomes cos omega c minus 2 omega mt minus pi and so many terms. So basically, if you see, I have very terms. So this is for n equal to 0. This is for n equal to 1. This is for n equal to minus 1. This is for n equal to 2. And this is for n equal to minus 2. And so on. Okay. So if I see, I have got various frequencies. So first is the carrier. Okay. And then we have another frequency, which is what we call the omega c minus omega m. Okay. Just like we have in the AM and omega c plus omega m. But that time we had only the first two frequencies and the carrier J. But now we have many other frequencies, omega c plus 2 omega m, omega c minus 2 omega m, omega c plus 3 omega m, omega c minus 3 omega m, and so many frequencies. That means here my bandwidth requirement, which was earlier because I was having omega m only, my bandwidth was twice of mm, it has got an infinite bandwidth. So basically, theoretically, your FM signal has infinite bandwidth. FM signal has infinite bandwidth because I have various frequencies, FC plus minus FM, FC plus minus twice of FM, and so on. I can write down one more, FC plus minus thrice of FM, and so on. And the carrier frequency. So you have got so many frequencies, and we know that my information is also contained in the sideband. Okay. Now here my information is contained in the sideband, so I have infinite bandwidth. So ideally I need a infinite bandwidth, which you can say it is not a good sign. Okay. So let's understand this thing slightly better. So this we got it. Okay. If you recall my last lecture, in last lecture, I have got this expression on slide number 10. If you see this slide number 10, it was the same expression, but now I slightly started with this Bessel function. So this is the same equation. I will write here.
Sir, sorry to interrupt you.
1 minute, 1 minute. Recall, it is the same equation on slide 10 of last lecture. Yes, yes, please. Before I go ahead. Yes, please.
Sir, the minus pi by 2 plus pi by 2, like pi argument would not be in the cos wala bracket.
That will change. That will change. But see, we are not concerned about that. We are concerned about what frequencies are getting generated. Okay. So omega C minus omega m, omega C plus omega m, omega. When we do the frequency spectrum analysis, okay, or the mathematical analysis, as I told you, mathematical analysis is also called the spectrum analysis. And the spectrum is always dealing with the frequency spectrum. So I'm more concerned what frequencies I'm getting in the output. Like in the AM, I got omega C minus omega m, and omega C plus omega. Forget about the plus pi and minus pi, or plus pi by 2 or minus pi by 2. That will change from cos to sine, but sinusoidal will remain the same. But my frequencies are the frequency values. I'm more concerned about it. So what frequencies are generated? I will get a original carrier, say 100 kilohertz. If my message signal is 10 kilohertz, I will get 100, 90, 110. Then 100, 100, 90, 110. Also, I'll get 80 and 120. Also, I will get 70 and 130, then 60 and 140, and so on. So many frequencies will be generated, as we'll see later on, that if I see the bandwidth now, theoretically, my FM signal requires an infinite bandwidth, because it is a function of a sine of a sine function, or a cos of a cos function. So this is the same equation, if you recall, we had in the slide number 10 of last one. So I just made it more clear how we got it. But if I see the Bessel function and its solution, it is given by this one. Now, please note that again, Bessel function point of view, again. So my emphasis is on this slide, that you are getting the 4 frequencies, infinite number of frequencies. Okay. So, which I put in the red color. Now here, again, as I said, no need to mug up what I'm writing now. Where? Because these are mostly used as appendix. What we have learned in the Bessel function, it is an appendix in most of the books, but I'm reproducing here for this one, where amplitude of the side frequencies, okay, J and M. Jn. This is the amplitude part of the Bessel coefficient. Jn, okay, can be converted to something like this. Again, no need to remember. Just I'm giving you, because last time I gave you the values of the table, various values of J0M as a table form. But it is also available in equation form. Again, as I said, no need to mug up those values, and no need to mug up this equation. Even I will not be able to remember. But just to give you an idea, it is m by 2 square 1 factorial n plus 1 factorial, okay, plus m by 2 4 2 factorial n plus 2 factorial. I would have avoided this, but my instinct was not allowing to just give like this. So there is a Bessel function, as I told you, given by this first equation in the slide. We compare with our FM equation, see what are the parameters which are matching. Alpha is equal to omega C and beta is equal to omega M. And on the same line, what we had the solution as an expanded series, I solved it. So we got this expression. Last time I just simply put the expression. Okay. So this is how we have this amplitude part, which is the J and M part. So it becomes m by 2 6, and then factorial 3 and n plus 3 factorial, and so on, which I will not continue. So just for your understanding, this is your factorial, which you all know that n is equal to J, or number of side frequency. M here turns out to be your modulation index, as we see later on. Okay. Now, we got this. And these values, as I said, could be in the form of a table, or could be in the form of a graph. In the previous slide, if you see, we have a table. Like last time we had a table. Let me see. Okay. Now, these things could be, as we have seen here, it is reproduced in the form of a table. Let me see. There is a table. Okay, I could not recall. Okay, so this was, and if I got these things, these values for various values of M, okay, are given in table, which was there in the slide number 12 of last lecture. Okay, so we put in the tabular form 0. I took M equal to 0, M equal to 0.5, M equal to 1, M equal to 1.5, M equal to 2, M equal to 2.5, and many could be there. And if you recall, in that there were certain values, like if I for M equal to 0, let me see, or sometimes these values, if you see in the books, because what book you are referring to, they are also put in the graphical form. Again, no need to mug up. So graphical form was something like this, if I recall. It was something like this. So this is equal to M, which is my modulation index here, delta F over FM. Okay. This is my 0. And let's say it is plus 1. And it is minus 0.1, minus 0.2, minus 0.3, minus 0.4. So various values are available. So if I take J01, so J0M will be something like this. That will go on decreasing the amplitude. So this is corresponds to J0M, that is M equal to 0, which is my carrier. For the first frequency, the carrier frequency has got the amplitude J0, as you see here, which you have seen here in this equation. This is my carrier. So this is, if I see here, I will write out here also. So this is my carrier. This is the first upper side frequency, first lower side frequency, second upper side frequency, second lower side frequency. Okay, so the amplitude of the carrier is J0, and J1 is the amplitude of the first side, and the J2 is the amplitude of the second side frequencies, and so on. So if you, so this is in the graphical form, because sometimes you will find this thing. So J0 is this one. So N is equal to carrier. Then we'll have another one which is corresponds to, I'm not very clear in drawing this thing, but yes, these type of the graphs are available. So there is another one which corresponds to J1M, that is N equal to 1 for first side frequencies. And then we'll have another one which could be for the second one. Let's mark with this another one. So there could be another one which is something like this, which is basically J2M, that is N equal to 2 for second side frequency. So this is just for your understanding that either the Bessel function could be given in the form of an equation, amplitudes here, or in the form of the table, which was the slide 12 of the last lecture, or it could be in the form of a graph also. Okay, but table is a very good form because it directly gives you the value rather than depicting from the graph. So just to forget about these things in the sense graphical and nothing. But yes, if you find something, don't be afraid. What is this? And we were never taught like this. So there is something like this. Now, if you see here, there's some important conclusion, what we see here in the next slide. So first thing is for M equal to 0, as we have seen in that table, okay, no modulation, because M also defines by modulation. M equal to 0, that means no modulation. That means it implies that only carrier J0 is present. and no side frequencies are present. No side frequencies are present. And also J0 is equal to 1. Okay. That means full value. Okay. So obviously, if you see the last tables, so when we are talking about this one, you see the, I will write down here, refer table on slide 12 of last lecture. Okay. So this is the first observation that we got it. Okay. Because as we have seen here, 1 minute. Okay. So that is the one. Now, I have not put m equal to 0.25 there, but for m equal to 0.25, also there are values are there. Let me see. I have to get value. Just 1 minute. Yes. Let me put again. I think this will be better. I will waste 2 more minutes, but it becomes very clear. So I'll put it like this. So M, then we have J0, J1, J2, J3, J4, J5. Okay, just reproducing slightly in a different form. Okay, so 0, and it was 1.00. No components were here. Okay, so that was a point for m equal to 0. There was no modulation. Only carrier amplitude was there. J0. J0 is the carrier amplitudes. Okay, so this is the carrier. This is the first side frequency. Amplitude. This is the carrier amplitude. This is the second side frequency, lower or upper, and so on. And these are also called the Bessel coefficients. Okay, and this is what we call the modulation index or the Bessel function of order and mammoth kind. Okay, I have one more 0.25. Okay, if you see 0.25, I will get 0.98. Okay, and this value is 0.12, and nothing will be here. Let's take 0.5. It is 0.94. It is the same thing which I was putting in the 4 digits. Now it is in the 2 digits, rounded off. So this is 0.24. This is 0.03. You will get in any of the books, and none will be available here. And I could have many more. Let's see how these things will be there. 1 minute. Just 1 minute, please. Okay. Then we have 1.0. I'll put it some more values, 0.77, 0.44, 0.11, 0.02, and nothing will be here. Last time this was not there, so I just put it here. There is a reason for that. And then I will add this one more, which is, let's say, 2.0. 2.0, it was 0.22 and 0.58. So don't worry, there was slight differences in the value because these are rounded off. 0.35, 0.13, 0.03. Okay. And then we'll have much more, 2.4, 2.5. Now, in 2.4, this value becomes 0, and we'll have certain values here, 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 and here also, which I could not recall. It is not there with me. And here, but certain things I wanted to explain to you. 0.50, 0.45, 0.22, 0.07, and 0.02. And there are certain more. I will take 5.5, 8.65. Again, here it is 0, 0, but there are certain values here, here, and so on. Basically, what we see here, if you see this table, this is uh, for the side frequencies, amplitude of the side frequencies. If you see here, there are three frequencies. If I see here, I put it by this color, 1, 2, and 3. There are three frequencies for which all power lies in side bands, no power in the carrier. There is no power in the carrier. And in this one, which I have marked as black, that means all power in carrier. All power in carrier. Obviously, no modulation means my all power was in the carrier, and no side frequencies, that means no modulation. So that is all power. But there are certain values of modulation index where, like 2.4, 5.5, and 8.65, where there is no carrier power and all the power is in side frequencies, okay, which is good for us because this is like your double sideband suppressed carrier. And there is another case which I am highlighting in a different color, which is this one. That means 0.25, if I say the power is in the carrier and the two side frequencies, first two side frequencies, and no other side frequencies exist. That means for m equal to 2.5, it is closest to the AM modulation. So it is just like your AM. AM also we got the carrier power and maximum power was there in the carrier and two side frequencies were there. So here also two side frequencies are there corresponding to amplitude of J1, 0.12, and the power is in the carrier. So from the side frequencies point of view, if I have m equal to 0.25, I will have a carrier and the two side frequencies. But there are certain values of modulation index in blue color where there is no carrier power. So I will just summarize. So black one I have already summarized in this one. Now coming to the yellow color. So I'll put the yellow color. And in the yellow color, what we see, here, for m equal to 0.25, I have got the carrier amplitude of 0.98, okay, and two side frequencies plus minus f1 of amplitude 0.12 each. Okay, so here it is like I am getting a carrier, I am getting two side frequencies, fc minus fm and fc plus fm. So it looks like it is the closest to AM. It is closest to AM, where we have one carrier and the two side frequencies. And then we have the third one, which I go to the previous slide, I highlighted in blue color. Now, if I have the same blue color here, for m equal to 2.4, 5.5, 8.65, if we see here, all power lies in side frequencies and no power in carrier. Okay, because as G0 is equal to 0 and there could be many power. So this is the thing. Please note that in some books, M or it is given as beta in some books. So don't be worry about that because that is with this regard to the AM this thing. So this is what we important thing is what we have learned here, that M equal to 2.5 requires same bandwidth as AM transmission. This is a very important question, is asked in various places. For FM transmission is nearly require the same bandwidth as AM transmission if my M is equal to 2.5 for FM. Okay, so that is a very important conclusion that we have seen from here. So this is the various important conclusions that we got it. We'll use this table in understanding how the signal is getting transmitted in my next lecture. Okay, so I have in today's lectures we discussed two parts. One, how we can generate a double sideband suppressed carrier modulator, which is basically a modulator, AM modulator, and then from that how to remove the one of the sideband also, and that is possible using a filter and so on, band pass filter and so on. And then we continued with the previous class, but now more from the Bessel function of point of view, which I just put this equation straight. But I now put the actual Bessel function, actual amplitude is the Bessel function in mathematical form, in tabular form, in graphical form. But no need to remember. Normally, we try to follow the Bessel function, which is in the tabular form, as we discussed, as we have seen here. Because then you can straight pick up the values from here. Okay, so whenever a problem is given, whatever the problems we will solve using this one, you will be provided with these tables. So please note that no need to mug up the table, the equation, the Bessel function, but just to give an idea how a Bessel function can be used to solve a function like sine of a sine function, what we encountered in a FM modulated signal. Okay, so I just stop it here and we'll continue with this next thing in the next lecture. Okay, any doubt? Any doubt? Let me see in the chat box, nothing. So I save it and save these two files as lecture A and B of today's date only, so that you don't get confused, because there's B is continuation of my previous lecture. And I stop recording, share this thing with you today itself. Okay, fine. There is no doubt. Any doubt? No doubt here. Let me see. So I stop the recording. Okay.